Next speaker.
Thank you, Dr. Mi Lai's excellent talk on robotic technology. It's my great pleasure to introduce the second speaker, Yi-Hua Lai. She received her bachelor degree in interdisciplinary program of science, including the physics and electrical engineering from National Tsinghua University in Taiwan, where she awarded the honorary membership of a 505 Scholarly Honor Society. Yi-Hua is a PhD candidate at the University of Maryland, College Park. She did extensive research work in experiments with her past experiment background. Yi-Hua's goal is to bridge the gap between the theories and the experiments. So let's welcome Yi-Hua Lai's talk on the progress of quantum computation on the Majorana nanowire. Let's welcome Yi-Hua Lai's talk. Thank you very much.
Thank you for your introduction. Let me share my screen.
Good morning, everyone. I'm Yi-Hua Lai. It is my honor to share my research on Miranda nanowire today. Miranda nanowire is the topological quantum computing system that Microsoft has been working on. First of all, I would like to introduce myself. I'm born in Hsinchu, Taiwan. Before I came to USA for my PhD studies, I got my bachelor's degree and master's degree in National Tsinghua University. My master's degree's research is on rubidium atom system that uses the interaction between atoms and light to implement quantum information storage. I conducted experiments and theoretically modeled the atomic system. When I came to University of Maryland, I switched my field from AMO system to solid-state system, particularly on Miranda nanowire. So far, I had several sub-studies, including non-local correlation, Coulomb blockade effect, and quality of quantization. Even though the research system that I studied in Taiwan and USA are different, they are both potential quantum computing systems that I've been dreaming to realize one day. As a theorist who has experience doing experiments, I realized how important it is to have theories and experiments help each other. Therefore, the goal of my research mostly focuses on explaining the experiments or proposing the new methods for the experiments. Scientists have been pursuing to realize quantum computing for more than a decade. But what is quantum computer? Quantum computers are the machines that uses the properties of quantum physics to store data and perform computations. Classical computers encode information in binary bits that can be either 0 or 1. In a quantum computer, the corresponding basic unit is called quantum bit or qubit. One of the special properties of qubit is its quantum superposition, that is the ability to simultaneously in multiple states. For example, this psi is a combination of state 0 and state 1 that can be displayed in this block sphere. Psi is located at one spot on the sphere, which is neither state 0 or state 1. Similarly, if there are multiple states, one qubit can be expressed as a combination of all the states. If the qubit has m states, then n qubit can represent m to the order of n numbers, which is exponentially larger than the classical bit. The physical examples of qubits can be the spin of the electron or the orientation of the photon. The other special property of qubit is quantum entanglement. This means there is a pair of qubits existing in a single quantum state. Changing the state of one of the qubits will instantaneously change the state of the other one in a predictable way. This happens even if they are separated by a very long distance. You might ask, why do we need quantum computation? There are several advantages. First, quantum supremacy. A quantum device can solve a problem that no classical computer can solve in any physical amount of time. Second, with superposition, multiple states can happen at the same time, reducing data crunching time. Third, speed up for certain types of problems, such as Shor's algorithm, Grover's algorithm, integer factorization, and optimization. Fourth, quantum computer can model quantum systems down to molecular level. Volkswagen and Daimler are using quantum computers to simulate the chemical composition of electrical vehicle batteries to help find new ways to improve their performance, and pharmaceutical companies are leveraging them to analyze and compare compounds that could lead to the creation of new drugs. So quantum computer has a lot of applications. What do you need to build a quantum computer? Firstly, quantum computer needs to be manipulable to implement different operations on quantum information. Then the stored information also needs to host a high coherence time, meaning the information maintains in the state for a long time rather than bounces back to the other state. At the same time, the quantum computer needs to be fault tolerant, meaning the system needs to be robust against the environmental disturbance. If the environmental noise already deteriorates the stored information, it is important to develop error correction methods to correct the information back. Here is an example why scientists use atomic and optical systems to implement quantum computing. Light is the information in the system because light does not have so much interaction with the environment. On the other hand, the interaction between atoms and light is strong, which makes the atomic system ideal to implement quantum operations and quantum storage. There are many big tech companies and startups working on building quantum computers now. Here are some typical platforms companies use, like Google Sycamore, IBM, Rejetta use superconducting processors or circuits. IonQ and Honeywell, they use trap ion. Intel use silicon spin qubit. Psi Quantum use silicon photonic chips. Cold quantum and atom computing use cold atom. Microsoft use Miranda nanowire. So far, Microsoft is the only company that invests in a topological platform, which hasn't found the qubit, facing big experimental challenges. But there must be some benefits that topological quantum computing platform have that makes Microsoft and scientists still working on it. Many of the current implementation of qubits such as trapped ions and superconductors are highly susceptible to noise and decoherence, but topological quantum computer is very robust against the noise by the topological protection. When we implement quantum operations, we use non-abelian braiding to realize it. I will illustrate more about topological protection and non-abelian braiding in the next 3 slides. There are several candidates to be topological quantum computing platforms, including quantum Hall system, topological insulator, semiconductor heterostructure, non-central symmetric superconductors, and 1D superconducting semiconducting nanowire. This 1D nanowire is the system that Microsoft and our group focus on. Let's talk about topological protection. Topology is the concept in mathematics that characterizes items by how many holes an item has. The topology of an item can remain the same topology, even if it is continuously deformed. For example, a ball, an egg, and a vase belong to the same topology, because all of them do not have any hole. When the continuous deformation does not create another hole, the atom can remain the same topology. However, if the deformation surpasses some point such that a new hole is created, then the atom becomes another topology. For example, a ball can turn into a mug gradually by creating a new hole. They no longer belong to the same topology, but a mug and a donut belong to the same because they both have one hole. As you can see in this plot, glasses belong to the two-hole topology, and pretzel belong to the three-hole topology. In physics, we define the topology using Chern number as this formula. The topological protection means the topological item cannot easily change its topology by the environmental disturbance because of its topological property, which helps the quantum computing system stay stable. In this slide, I want to explain more about non-abelian braiding. In 3D world, there are two kinds of particles. One is fermion and the other is boson. When the two particles exchange their positions, the wave function of these two particles picks up an overall sign. If these two particles are fermions, then the sign is negative. If they are bosons, then the sign is positive. We can see both fermions and bosons can recover back to their original wave functions if the particles exchange positions twice. This property is called commutative. In topological quantum computing, a qubit is composed of a group of anyons. Anyon only exists in two dimensions, which picks on a phase with arbitrary beta. In this case, the wave function of two particles cannot change back when we switch their positions twice. This property of anyon is also called noncommutative or non-abelian. In the case of non-abelian statistics, exchange paths corresponding to different braids cannot be equivalent, even though the total widening might be the same. This plot gives an example. If we exchange 2 and 3 first before we exchange 1 and 2, the overall effect from this braiding is different than exchange 1 and 2 first before we exchange 2 and 3. On the left plot, the line corresponding to 2 is on top of line 1, and the line 1 is on top of line 3. On the other hand, the braiding on the right-hand side shows that the line 2 is on top of line 3 first, and then line 3 is on top of line 1. So these two braidings are different. Now it's time to introduce the 1D Majorana nanowire. The idea to store quantum information in Majorana fermions originates from LHC grid type. Even though we call it Majorana fermion, it is an anyon, not a fermion. Majorana fermions are particles identical to their own antiparticles, expressed by gamma equals gamma dagger. Majorana zero modes, which only exist when the energy is zero, are potential qubits for the quantum computer due to their topological protection, non-local nature, and non-abelian statistics. Majorana pair will appear on both ends of the nanowire as in the upper right plot. In 2010, the so-called Majorana nanowire was proposed, followed by a lot of theoretical and experimental studies. The Hamiltonian of the nanowire is as follows. It needs spin-orbit coupling, Zeeman field splitting, and the S-wave superconducting gap. The energy band will look like this plot. People are searching for the proof of existence of Majorana, such as zero bias peak, quantized conductance, non-local correlation, gap closing and reopening, and Majorana oscillations. Zero bias peak is the conductance peak appearing at zero energy, as you can see these pink signals in the experimental results. We can also see this part from the cross-section line cuts, as this part. Since Majorana zero mode exists only when energy is zero, it is essential to see the zero bias peak. It is theoretically predicted that the zero bias conductance peak should stick to the quantized value 2e squared over h in the zero temperature limit. My published work mainly rely on the non-local correlation. This PRB paper is my published work. Non-local correlation means when one end has 0 bias peak for Majorana, the other end must have 1 as well. The gap closing and reopening happens near TQPT field, as marked by yellow line. TQPT field distinguish non-topological region and topological region. We can see there is a check mark center at TQPT field. This is the gap closing and reopening evidence. Above TQPT, the red curve is the Majorana bound state. We can see it oscillates with the amplitude increasing as Zeeman field increases. This phenomenon is called Majorana oscillations. Unfortunately, Andre bound states, which are not topological at all, mimic Majorana bound states in different ways, such as the above A, B, C. Therefore, distinguish the Majorana bound states from Andre bound states has been an important issue. This slide shows the main results from my non-local correlation project. For your information, the parameters are listed as above. The only difference between the left set and the right set is that the chemical potential in the left set is 1 MeV, while the right one is 5 MeV. In this slide, the black dashed line in panels A, B, C belongs to TQPT field as the analytical expression here. Below this field is trivial region, or non-topological region, and above is topological region. Panel A is the energy spectrum. Panel B is the conductance color plot from left end, and panel C is the conductance plot from the right end. Let's use the mu equals 5 MeV case as an example first. We get 2 line cuts from this color plot. One is at yellow dashed line. We take the line cut from panel B and panel C and put them into panel D. The blue solid line is from left end and the orange dashed line from the right end. We can see there is no correlation for the conductance peak, even though we see 0 bias peak from the left end. The wave function cannot be separated either, as in panel F. In this slide, the 0 bias peak is produced by Andre bound states. Next, we take another line cut, the purple dashed line from panel B and panel C, and then combine them into panel E. In this case, we have confidence that we are in topological region because we can see the 0 bias peaks are overlapping and correlated with each other. We can further check the wave functions as in panel G. The Majorana modes are separated on both ends of the wire. In the mu equals 1 MeV case, we take line cuts only above TQPT field, so the 0 bias peaks are correlated and Majorana modes are well separated. Now I would like to talk more about Coulomb blockade project, which has been published in Physical Review B this month. Coulomb blockade exists in small systems, where the transport of electrons need to overcome the Coulomb repulsion. The system is viewed as a quantum dot with charging energy. Only when the energies in the dot and the outside reservoirs match can the transport occur. Coupled pair handling can produce 2e periodic conductance oscillations in the Coulomb blockaded superconductor, while the single electron transport can produce 1e periodic conductance oscillations in the Coulomb blockaded normal metal. In the superconducting system, one can weaken the superconducting gap by increasing the Zeeman field. Then the curve will move from blue to green and green to red. We will be able to see the transition from 2e periodicity to 1e periodicity. Our motivation is mainly in the experimental papers by Sean et al. In 2018 and Albridge et al. In 2016. We want to constrain a nanowire model by referring to the experimental data. There are some prominent features in the experimental results. First, current blockade conductance shows bright pattern. Second, oscillations of conductance peak spacing, showed as OCPS, decreases with Zeeman field, as you can see in this panel. Finally, the first OCPS amplitude shows length dependence, as this plot. Here are more experimental results. We can see the 2E periodic peak becomes 1E periodic peak as the magnetic field increases. OCPS is obtained by tracking the peak of the 2D conductance plot for the even and odd parities, and then calculating the spacing between them. We can see the OCPS is decreasing. As to the right plot, this bright pattern becomes more obvious in the longer wire case. Here are some motivations from theoretical side. First, solving the master equations as earlier work requires heavy computational load that we can only include less than 10 energy levels. Second, here are some realistic effects not considered in the earlier work. In this slide, I show the standard Hamiltonian of the 1D superconducting nanowire with quantum dot, lead, and tunnel barrier. Since this is a standard recipe, I will move on to the next slide. We derived the generalized Meyer-Wingren formula from the red equation. Coincidentally, this gamma is the result of Meyer and Wingren's work for a one-terminal system. We can further simplify this gamma by the conservation of fermion parity. Then the form of gamma becomes computational efficient that we can include thousands of states. In this slide, the left side is our numerical results that's most similar to the experimental data. Panel A is the current blockade conductance as a function of gate voltage and Zeeman field. We can see this darkness and brightness look similar to the experimental result, starting from B star. Panel B is the regular conductance without current blockade. Panel C is the energy spectrum. Panel D is the OCPS obtained from panel A. The first dashed line marks the TQPT field. So in our model, we can see the decreasing OCPS mainly comes from the multiple subgate states in the trivial region. One notable advantage of current blockade OCPS is that it projects the energy levels from both ends of the nanowire, while the regular local conductance can only show energy levels at one end. We also show different parameter dependencies in our paper, but due to the time limit, I only show the most important results today. Here are the highlights of our current blockade work. We've derived the generalized Meyer-Wingren's formula and applied it to the current blockade nanowire with all the important realistic effects. We can also distinguish the 1E periodic transport between Miranda bound states and normal metal states by their temperature dependence. We also numerically show and explain the bright pattern and the decreasing OCPS. Finally, the decreasing OCPS mainly comes from the Andre bound states in our model, which does not show length dependence. Now I would like to talk a bit about my ongoing project on the quality of quantized conductance. In 2018, the experimental group led by Professor Cohen-Hoven published a Nature paper claiming they saw the well-quantized conductance plateau at 2E squared over h and interpreting this as an evidence for the existence of Miranda zero modes. However, several inconsistencies were pointed out by Sergei Frolov and Vincent Morick between the raw measurement data that was made available to them and the figures that are published in the paper. The authors found that their data has calibration issue. After they fixed the calibration, The new conductance calibration shifted the plateau values by 8% above 2e²/h, which affects all the figures. When the data are replotted over the 4-parameter range, including the ranges that were not made available earlier, points are outside the 2 sigma error bars. The authors can therefore no longer claim the observation of quantized Majorana conductance. Therefore, they retracted this paper. This paper is published by our group, showing that the quantized conductance can be demonstrated in the non-topological region by the smooth potential variations and disorder-induced subgate bound states. This means the quantized plateau can be created by fine-tuning the impurity in the nanowire. It does not necessarily need Majorana zero mode. In my current project, we want to distinguish the Majorana zero mode from other non-topological subgate states by defining a new quality factor for quantization. We can plot the zero bias conductance versus the normal metal conductance. Within the well-quantized range, let's say within 5% of the quantized value, we can find the minimum and maximum of the normal metal conductance that sets the boundaries for the well-quantized range. Then we take the ratio of the maximum and the minimum to define F. For a situation where the well-quantized range is wide, the ratio F is also big. Similar for the definition of J, but J is defined over Zeeman field Vz. We try to calculate F and J in different setups as the left plot. We intend to distinguish the Majorana bound states by the difference of F and J values. Here are my preliminary results for the good zero bias peak case. Since we are still in preparation for publishing these results, I won't explain too much. Right now, the important issue to discover and identify the Majorana qubits lies on the experimental groups. From Professor Shankar Dasama and Professor Leo Hoven's invited talks in March meeting this year, they both commented that the material for the nanowire should be purified before they can find the Majorana qubits. Otherwise, as I've discussed in this talk, disorder could mimic the signals for Majorana qubits. There are also some secondary experiments that can be done, such as non-local conductance measurement. In the current blockade nanowire experiments, one can use temperature dependence to distinguish one periodic peak between Majorana bound states and normal metal states. Currently, theorists are still proposing new methods or arguments to help distinguish Majorana bound states and Andre bound states in the experiments. But until the experimentalists have clean material to search for Majorana qubits, theories are just armchair strategies. Last but not least, I want to thank my advisors, Professor Jaydeep Saul and Professor Shankar Dasama, for their guidance in this work. Thank you for your attention. I plan to graduate in 2022 summer. Right now, I'm looking for industrial positions in quantum computing companies or postdoc positions focusing on quantum computing. If you are interested in my talk, you can contact me through my LinkedIn and email here for further discussion. Thank you again.